Today, we are communicating inside Microsoft using Microsoft Teams, and the speech enhancement pipeline is based on deep learning and is also created in my team. Now we can do a lot of things impossible before. So I cannot tell you 2 or 5 years, but I can tell you that I see it in an observable future, having a brain-computer interfaces components in the human-machine interface of devices we use every day.
So, welcome to the IDUN Technologies podcast. We're very happy to have Ivan Tasha with us today from Microsoft Research. Ivan, thank you very much for joining us. It's really a pleasure to have you here and to have your perspective on what's happening in the world and technology.
Thank you for the invitation, Mark.
So it's really interesting. You know, at IDUN, we're still a relatively small startup working in neurotechnology and in-ear EEG. And it's always a pleasure to talk with people who've been really building these types of technologies and industries over decades. I think many people might not realize the impact you've had on audio, Microsoft, all these different devices like the Kinect. Can you give us a quick intro into what you've achieved so far?
Hey, my name is Ivan Tashev, and I'm partner software architect in Microsoft Research, leading audio and acoustics research group. My interests are in general signal processing using machine learning and artificial intelligence. I have had a lot of fun projects in my career. I'm blessed with that. But still remember one of the milestones in my career was working on the audio pipeline and the speech enhancement pipeline in Kinect, mostly because most of my research community was absolutely convinced that this is not possible. It cannot be done. And there was a plenty of fun to work on the creation of one of the important components in a device, which later set the Guinness Book of Record for the fastest selling electronic device in the history of mankind. And after this, naturally became working on the speech enhancement and spatial audio algorithms for HoloLens. And today, we are communicating inside Microsoft using Microsoft Teams, and the speech enhancement pipeline is based on deep learning and is also created in my team. And this is kind of the you feel rewarded for your work in the industry when you change the lives of hundreds of thousands, even millions of people. Since quite a while, 2018, me and my team are involved in brain-computer interfaces project. And we're really curious to see what can be done with good signal processing using artificial intelligence there.
Yeah, it's really interesting. You know, when I think about also when I was transitioning from more engineering, getting into more things like interactive design, the Kinect was really such a doorway for so many people because you could really work with the depth map, you could, extract 3D models, you could really, it was a way for machines to really start to see the world, and people could, like me, could actually understand it, work with code bases. And when I was also getting into first photography and then transitioning from photography into some film projects, the first thing you learn is that sound really is half of the movie. And you really forget about that because so much of the world is biased towards, let's say, visual stimuli. And we think about that as one of the first things. Also, when we think about products and design. And then the audio is always this underlying feature which actually brings so much richness to the human experience, but somehow we don't always put it at the forefront of product development. How was it for you?
Let's look at Mother Nature. The size of the visual cortex is maybe 30-40% larger than the size of two auditory cortexes in the brain. So Mother Nature gave us quite equal brain power to process the visual stimuli and the auditory stimuli. And
Mhm.
then you go and you have to create a computer game, and the audio people have 10% of the computational budget. That's not fair.
Exactly. I mean, why do you think that is? Why do you think that the visual part has been dominating so parts of technology industries over the past decades?
In general, our algorithms for visual processing require more computing power than for audio processing.
Hmm.
And this is what caused adding more resources for visual processing. Even GPUs appeared as processing of the imagery
Hmm.
because the main computer couldn't do it in real time.
Hmm.
On the other hand, in a video call or in a movie, if you skip a video frame, nobody will notice. If you skip one audio frame, and everybody will hear it. But still, somehow we take it for granted.
Yeah, it's also interesting. I mean, if you look at movies, you know, you're traditionally shooting at about 24 frames per second, and it's slower than real life. But because it's been in a movie, you feel like there's this movie quality, and the movie quality is actually much less than what we experience. But the audio has to maintain good, crystal clear characteristics to actually immerse you into the story. So it's also, yeah, it's really interesting to think about that. You know, the audio is really what gives you this tangibility to a lot of immersive experiences. And I've always been
Absolutely.
well, and also when you start to think about, you know, transition to brain computer interfaces, you know, I think back to if I'm doing some audio engineering, I'm looking at a spectrogram of an audio soundscape, I'm looking at noise, I'm looking at how to boost certain signals, extract certain features. And then you start developing brain computer interfaces, and once again, you're oftentimes working with colorful spectrograms as the map of what happened in an experience. So when you're now going from audio to brain computer interfaces, what is this transition like for you?
Actually, this is not a quite large transition because
Hmm.
first, I specialized back in the Technical University of Sofia in Bulgaria, medical electronic equipment.
Mm.
And I actually was assistant professor there before to join Microsoft, and I was teaching signal processing to students which specialize in medical electronic equipment. Just my last paper about processing electroencephalographic signals was published in 1991 till 2018, when I kind of returned to that field.
Hmm.
And also in my team, portion of people who are part of the brain computer interfaces project also have been in one or another stage of their careers processing biological signals, collecting data from real subjects, etc., etc. So we didn't start from scratch, from zero.
Hmm.
Most of us had certain experience of processing biological signals and taking signals from alive people, from humans.
Hmm. Yeah, and I mean, when we talk about brain computer interfaces, you know, many times it's interesting. In many conversations I've had recently, people talk about the influences we've had from science fiction. They talk about invasive brain computer interfaces like Neuralink. And it forms a certain picture in society, I feel, about what we think a brain computer interface is or can be or will be in the future. So when you say brain computer interface, what comes to your mind? What are you thinking about?
And computer interfaces is a very broad thing.
Hmm.
And there are a lot of perceptions which depends on where you are looking at them. I work in Microsoft Corporation when we do computer software. From this standpoint, we look at the brain-computer interfaces as one of the components, one of the modalities of the entire human-computer interface,
Hmm.
which has to be used when it is more convenient for the user. You cannot force me sitting in my office with a nice keyboard in front of me and a mouse and a large display to use brain-computer interface. That's less convenient. That's something we can create, but users, people are not going to use it. Same thing happened with speech recognition. Let me give you this example. The speech community for many years told that speech to text dictation is the main scenario. And at least for Microsoft Corporation, it ended up when in Windows Vista, we released a pretty much perfect speech recognizer with using a closed-talk microphone. And this was so seamlessly integrated into Microsoft Word. It was a perfect dictation machine. Nobody used it because still typing is more convenient. Yes, you can dictate faster, but from the moment you have to send commands for formatting, new paragraph, underline, boldface, etc., then still the keyboard is a better choice. Happened that speech recognition, the key application is on devices which don't have keyboard and mouse. Mobile phones, wearable devices, when that's the only or at least the most convenient input modality. Same thing applies to brain-computer interfaces. Our community of people who work on brain-computer interfaces have to find scenarios when brain-computer interfaces are most convenient for all of those who are using them. And also, we should basically clearly understand that we don't work on brain-computer interfaces for the sake of brain-computer interfaces. That BCI is just part of the entire human-computer interface system, one of the input modalities, and they should be used alternatively with other modalities when it is more convenient. So this is one of the things which should be clearly understand if you're talking in general of human brain, talking directly to the computer. With the time, when those technologies are getting better and better, then you will have more and more scenarios when brain-computer interface will be preferable. But for now, we're looking the best for the best scenarios when it is the most convenient or the only possible scenario modality for human-computer interface.
And at this point in time, are there specific points where you see brain-computer interface as the only solution to achieve some sort of user goal?
So again, it depends on the context. When we created this brain-computer interfaces project in Microsoft Research, we got together 7 researchers in Microsoft Research and decided, okay, what we're going to do. And then we put certain general directions for our project. And the first was, we are working on brain-computer interfaces for the general population. And this directly means non-invasive methods. There is no sane person with normal health which will allow us to open the skull or drill holes in that skull. Also, this means that we have to deal with a smaller number of electrodes. We don't believe that the person of the future is going to walk down the street wearing a 64-channel EEG cap. And also, the third point is that those electrodes have to be integrated into everyday things we already wear on our head, like headphones, like earbuds, like glasses, like virtual reality glasses, like augmented reality glasses, or at least they should look like something like this. And actually, we do have a design which contains in-ear electrodes. They go behind the ears, and the electronic is back on the neck. And it looks like a Bluetooth headset. There are such designs. Yes, this is a BCI device, but there is nothing alarming, nothing extraordinary in wearing that device. And we believe that this is pretty much the way to go, not exposing drastically the brain-computer interface device, integrating seamlessly, almost invisible, the electrodes into the device you already wear on our heads.
Yeah, I'm also thinking, when you talk about applications and consumer use cases and different technologies, of course, everyone is talking about artificial intelligence. I think for me, I'm really interested in this idea that in the future, when we're defining the reality for a person, even I think we even do that now also with audio. We've seen how audio systems get so much better over the past couple of years, and we've gotten so much better, where you have clearer audio. Sometimes I'll be in a busy train and I'll ask the person on the other line if they can even hear me, and they hear me clearly, because my personal soundscape and what is actually delivered to them is now different. It's almost like a different reality. And I guess that reality is oftentimes being created by artificial intelligence algorithms. And I'm wondering in the future if we'll be doing things like real-time voice modification. So if I want to make my voice sound nicer or more aggressive, depending on who I'm talking to, I'll just flip a switch on my phone and it'll put my authoritative voice into a conversation, or it'll put my soft voice into a conversation. And it seems like brain-computer interfaces play a part of that, and potentially recognizing emotions or recognizing focus or fatigue. So do you see these technologies developing independently from one another, or do you think there's going to be a lot of synergy between AI and VCIs?
Oh, first, Mark, I don't want to alarm you, but we can do this right now with the voice morphing. I mean,
Good to know.
oh, look, artificial intelligence is a very powerful tool. In general, if you make a step back, there are three technology enablers of brain-computer interfaces. The reason we started to talk about this now. The first is actually microelectronics. Back then, 20, 30 years ago, to put electrodes on a human body for whatever, electrocardiography, electroencephalography, whatever you do, your device had to meet a very strict requirements, especially the power supply. I remember 20,000 volts peak, 6,000 volts constant, so you don't fry your subject if there is something happens on the power net. And just the transformer of those devices was something very big and heavy. And suddenly, with microelectronics, we can have a half a cigarette pack size device which collects 64 channels and transmit them wirelessly to your computer. So all of the power supply problems solved. And this allows us to have our subjects to carry this device with them and to have a long-term collection of any kind of biological signals. The other thing I also clearly remember is that the electrodes are not the same. We had a small revolution in material science. We have new materials. We have 3D printed electrodes. We have new glues. We can put the electrode and it stays there on the human skin for hours. That was not the case before. We, after a certain amount of time, were getting bad signals. It was just not possible to wear any kind of electrode for a long term. And definitely the third enabler is the evolution in deep learning and artificial intelligence. Now we can do a lot of things impossible before. Even if you look at traditional machine learning classifiers like SVM or linear regression, they were not available before. Not only that, we didn't have a computers capable for doing this in real time. Today, SVM is kind of the regular tool. You try it first, and then if it works, you go and try to use some deep learning or artificial intelligence. And especially speaking about artificial intelligence, this revolution happened in front of my eyes, pretty much in signal processing. Anything we tried with the new deep learning methods worked better. Enabled us to do things impossible before. And with the computers that can do this in real time, now today with audio, with images, we can do things, even with text, we can do things impossible before. Absolutely the same revolution is coming in the sphere of biological signals. We also are witnessing a revolution, the transition from supervised training, when you have a bunch of data and a bunch of labels, and you literally tell the neural network, if you say this, produce this. That's good, but labeling is expensive. And the revolution which happens today, even in those months, is the transition from supervised to non-supervised learning. When you just dump a bunch of data to the neural network, and by defining a proper cost function, you train without labeling that data. And we know what happened when you train on all of the text in the entire internet. This is the GPT-4 model and the Chat GPT. The accumulation, increasing of the size of the neural network, considering the vast amount of data we have, brought a new quality. Literally, at some point, you saw that hockey stick when you increase the complexity and the neural network performs better and better. And at around 50 billion weights, it just skyrockets. And today, GPT-4 has more than 1 trillion weights. This is something we are going to see very soon in biological signals. Technically, putting all of the data we have collected, let's say electroencephalographic data, and creating a large model of the electroencephalographic signal, we will have something which already capable to extract the gist of the electroencephalographic signal, for example, and then use this as a future extractor to our task-specific classifier for emotion detection, attention, focus, sleep, etc., etc. This is a process we're seeing today, and we're going to witness in the upcoming months in less than a year.
Yeah, I mean, the way you describe it, I think back to the Connect. I mean, there were certain enabling technologies that came together which allowed you to really build this 3D camera system. And with BCIs, I definitely agree. I mean, the microelectronics materials, it allows us to really start to build devices which are like integratable into a consumer lifestyle like never before. So it's a super exciting time to be part of it. I mean, do you think we'll have a let's say the equivalent of the Connect as a BCI, something which is like very accessible to consumers, easy to use? Do you see this coming on the horizon for, let's say, the next 2 years, 5 years, or 10 years?
Integration of brain-computer interfaces component depends not only on the maturity of the technology, it also depends on the demand.
Yeah.
Let's take one particular scenario, HoloLens, and this is augmented reality glasses. So you put them on, and you can see on top of your real reality additional augmented object, and this is super useful for today of design work. You can see in 3D whatever you are designing, but also broadening the applications of those devices. From the moment they go to the manufacturing floor, we face a lot of challenges. First, the worker there holds tools and eventually protective gloves. So all of the gesture recognition we have, all of the controllers for the control of the devices are useless. Also, it is noisy there. And at some point, the voice control also will stop to work. And trust me, I know how good it is. My team created it. So at some point, we'll end up with brain-computer interfaces as one of the, or most probably the only modality for interaction with this device you're wearing on your head. And this is one of the potential scenarios when you will have to utilize this. And the progress in this will basically be tied with the speed of releasing of new models and the demand and proliferation of those devices. So again, it is not maturity of the base AI technology. Now we depend on who needs it and when the next product using it will be shipped. So I cannot tell you 2 or 5 years, but I can tell you that I see it in an observable future, having a brain-computer interfaces components in the human-machine interface of devices we use every day. It could be media player, which you wear on your arm while we're jogging, and you don't want to press the buttons for the next station, next song. Then this can be the EEG electrodes in your earbuds. It could be devices like HoloLens, the device for augmented reality. It could be something else. It could be something hidden or in your headphones. But overall, this is coming. And this is just strictly talking about general population. We didn't even touch the medical applications of brain-computer interfaces. Enabling people which are locked in their skull because they are paralyzed and they can communicate with the external world. And this is where I expect actually to see a lot of applications of brain-computer interfaces. Even something that looks kind of not that important, using brain-computer interfaces for biometrics. Getting biomarkers is, okay, you have Parkinson, how much? Just getting it accurately allows your physician to prescribe a proper medicine, the dose. Okay, this reduces your Parkinson with 1%. Let's add more of that. This is something which will enable people, a lot of them, to have a way more comfortable life than without using this brain-computer interface devices. So I see on the horizon how brain-computer interfaces will play an important role in treatment of all of neurophysiological diseases and will bring relief to a lot of people, way more than those chained on a wheelchair, which also will benefit from the brain-computer interfaces. I see on the horizon prosthetic limbs which are controlled entirely by your brain, and pretty much making you to have pretty much a prosthetic arm which you can control by brain, how in the same way as you control your live real arm. So there are plenty of applications, and again, we in Microsoft basically self-limited us to a specific direction, but I know plenty of smart people working in every possible direction for bringing brain-computer interfaces to people, improving their quality of life.
Yeah, I think also, that's one of the reasons why I love working in this area, this potential to have impacts at different levels of society. I mean, the things we're working on, we're currently have single channel in-ear EEG, and we know that we won't have amazing spatial resolution, but the ability to just track neuromarkers over time, the same way we can track things with a smartwatch and sort of complete this picture of motion, heart, and mind, I think is going to allow us to build some really good foundations also for degenerative disease, alongside the consumer application. So I'm always thinking, we're looking for good as solid, reliable applications for the consumer space, and then also use that as a foundation for looking at these more involved problems in society. And I mean, talking also about artificial or augmented reality, I kind of use that also as a marker, because I think back 20 years, 15 years, how augmented reality was proved pretty well with a few companies, a few startups. But it was always locked in like specific applications, like you have to download a specific mobile app before you could open up the augmented world around you. And then when you could bake a lot of that technology into the operating system of mobile devices, then it opens up really the use case to any developer where they can just interact through an API. And I think abstracting away the neuroscience from the development of brain-computer interfaces and use cases, which basically goes into what you said about the rise of deep learning and unsupervised learning for neuromarkers. I think it's going to be super impactful. I'm always just wondering what's the best way to make that accessible. Is it a situation where we have to have multiple companies fighting for GPU power so they can train their models faster than the competition? How do you see that part of the development phase? Because I think that's also one of the more difficult parts that a lot of companies are working on, where you need the data to train on an unsupervised model and to get the biomarker to prove the value, but you have to have the device in the market first to get the data. Like, do you see a way to get around this issue?
In general, this is the classic chicken and egg problem. This is the story of my life. Yes, we need more microphones to get a better sound capture on your laptop, on your computers. And the hardware makers say, okay, we'll put them, but there is no software to support this microphone array. And then the software makers like Microsoft say, wait a minute, why we should put microphone array support when there are no multiple microphones on the market? So same thing is with electroencephalographic signals and in biosignals. We already do have a lot of signals collected and publicly available. This allows us to train large neural networks. A lot of companies and academia actually feel that they are kind of left behind. Just a few large IT companies have those hundreds of thousands of GPUs to train a large language model like GPT today. But they're smart people. I'm pretty sure that in several years, we'll have models which are as good as GPT-4 today, which you can train on the computational resources available in any university or even in a small startup. Of course, at the time, large IT companies are going to do something even crazier with the hundreds of thousands of GPUs, but I don't think that this technology will remain, the large models and artificial intelligence will remain locked in the large IT companies. This is inevitable. Those guys who don't have the resources, okay, they don't have anything else to do than to invent a way, a neural network architecture, which can do the same job and to be trained to a fewer amount of resources, which they do have. Same thing is with biosignals. First, we don't have that much data. Even if you collect all of the EEG signals digitized by human civilization, I guess a good professional class computer with 4 or 8 GPUs will be able to manage it, to process it, and to create a large EEG model for us. So at least at this point, neither academia nor researchers and in startups are limited by the lack of large computing power.
Yeah, it's interesting. It's it's really challenging, like working in the BCI space when you try to build all these different components, the materials, the hardware, the platform, deep learning models. What advice do you have for, let's say, new neurotechnology companies and BCI companies that are being founded or were recently founded? What should we be working on?
Oh, everything. Starting with materials and 3D printing of new electrodes. going through microelectronics and using whatever is available. But most importantly, the investment that brings the biggest bang for the buck is learning AI and deep learning. This is something which brings difference in every task we have touched so far since we started to use deep neural network. In every single thing we are working on, audio processing, video processing, biosignals processing, every problem, every project, every task, we get consistently better results using neural network technology, using artificial intelligence technology. Okay, don't get me wrong, it is not the magic wand. If it doesn't work with SVM, it most probably is not going to work with deep neural network. If it does work with SVM classifier, almost for sure you'll get way better results using neural network. And frequently, this is the difference between not suitable for deployment or now ready for deployment and for use by the general population.
Just out of curiosity, do you have a favorite deep learning architecture that you just find beautiful?
Okay, we're starting another topic here. Frequently have been asked, okay, machine learning, deep learning, then you don't need the local expertise. And at least for now, this is deeply wrong. Domain experts, they bring deep knowledge about the nature of the signals being processed. Let's leave it to biosignals and audio signals. They can help first with the architecture of the neural network being used, because they know what is going to be processed. If you're a pure machine learning expert, you will try some technologies, but it will take time because you don't know what you're processing. The second thing is when you start to do the processing, you have to have certain cost function. Learning people usually use two. If they use minimum square errors, if this is a regression estimator, or maximum mutual information, if this is a classifier. In our practice, we use way more sophisticated function, which cost functions for training the neural network, which came from the nature of the process, from the type of the signal we're processing. And that's something which domain expert contribute. And especially in the case of supervised learning, of training your classifier, almost never you have sufficient amount of data and labels. Which means it is critical to do data augmentation. In audio, you can add various noises. In biosignals, you can also add artifacts, etc., multiplying up to 10-fold the amount of labeled data. To extend that in some cases, even if you do have 100,000 of hours of audio data, during the training process, this being augmented and changed, so the cost function estimator doesn't touch the same piece of data twice. And this is why domain experts are still important part of the process. Let machine learning people create a new architectures. They try for various tasks, but sooner or later, when you want to deploy the neural network that is usable by the broader audience, you have to talk with the local expert. Same thing is valid for biosignal processing. Biosignals, they have their own specifics, they have their own properties, which are known for the domain expert. So don't fire your neuroscientists yet. Don't count just on machine learning people.
Yeah, definitely. I mean, I think it's really a team effort between hardware, materials, domain, data science, and then also product development, user experience, and bringing everything together. I mean, it's been super, just inspiring and wonderful to talk with you today. It was really great to hear like your background, transition from audio to EEG, Any last thoughts? I mean, I think it's really cool the impact you've had in audio and what you'll certainly have in brain-computer interfaces.
Look, it is mostly addressing those who are just starting in the research field in neuroscience. What is super important is to do whatever you really like to do, whatever you really want to do. Then you get the results. Then you get the impact. Then you feel happy and your work matters for the others.
Oh, that's a beautiful way to bring it all together. IDUN, thank you very much. Again, it was really a pleasure to have you on the podcast. I look forward to future conversations and yeah, hopefully meeting up sometime and exchanging thoughts on brain-computer interfaces.
Thank you for the invitation, Mark.
Or through brain-computer interfaces. Cool. Thank you very much. We'll be in touch.
Yep. Bye-bye.